Hello, my name is Ahmed, and today I'll be presenting my simulation with my meshes. I'll be talking about how I conducted my residual, my volume fraction, and temperature graph, and give some information about the simulation. So in this slide, I'll be talking about my meshes, so my domain. I've conducted three type of meshes, so coarse, fine, extra fine at n, 2n, and 4n, as well as my element size, elements, and nodes. I've decreased my element size by 1 millimeter each time to make the squares smaller and smaller, and then obviously my elements and nodes increase each time. This were to find out how fine my mesh would be to if I were to decrease the element size, and I use those three for my simulation. So as for simulation setup, when I've chosen the PCM materials as properties as defined below, so density, specific heat, thermal conductivity, viscosity, latent heat, and melting temperature range. So for this, I check the silica-based encapsulation PCM material online, and I find those values. So I've added three screenshots of each from the simulation, how I set it up. So for general, I changed the values, and then for no for models I've turned on three of them. For materials, fluid, I added my PCM emitter of the air. For my cell zone and PCM, I added some of the properties there. For my boundary conditions, I changed my wall and then added my values to the generated heat, and for solution I added my temperature and volume fraction graph, and that was pretty much it. I initialized it and then run my simulation. I'll be talking about my residual graphs, so how the energy is converging. I've also done some select temperature counters, and I'll be talking about those diagrams. So for my all meshes, they all show some energy residual oscillation. This is normal because of the latent heat is released during the phase change. So for my cross mesh at N has larger fluctuations, so it starts really slow and then has larger fluctuations, which is less accurate of the tracking from the melting front. For my finer meshes at 2n and then 4n, there is smoother out and energy behavior, especially for 4n, which is more stable, and there is smaller oscillations happening towards end. So all of these, the energy is converging. As we can see from the residual plots, the cross mesh shows large energy fluctuations due to low resolutions. With finer meshes, energies will become more stable and also reduce significantly, especially for 4n. And then so we can conduct that the 4n mesh has a better energy convergence and is more stable. So for my select temperature visuals, I've done the three for my n, 2n, and 4n. As it can be seen that for my n, my mesh has burned more significantly as opposed to my 2n, which has burned after the same number of iterations. Unfortunately, my last one, I lost my somehow I didn't get any burning, which probably was a fault, but that would have been a smaller burning phase as well. It would have been much less. In this slide, I'll be talking about my volume fraction and then temperature graphs. So as it can be seen from my volume fraction graphs and my temperature graphs, they all look pretty much the same. So for my volume fraction, it increased over time for all three meshes. In this case, for my coarse mesh, so I've run 10,800 steps seconds, which is 3 hours. And for my coarse mesh, it took about 7,122 for volume fraction to reach one, so to fully melt. For my fine mesh, it took 7,187 seconds, and for my extra fine and it took 7,251 steps for the volume fraction to reach one. So for my temperature graphs, temperature gradually increased for all cases, stabilizing at 310 Kelvin. Despite different melting times, all meshes reach a similar final temperature because we set the temperature at 310 Kelvin and I was trying to run the simulation, so it reached 310. It's all pretty much similar at 310, and it can be seen the straight line from each. It reached 310 Kelvin. So these two tables, these six tables, show that the coarse mesh melts faster but can slightly overestimate the speed of melting due to the low resolution. Finer meshes give slightly delayed but more accurate thermal behavior, which is matching the real world physical expectations better. Because coarse meshes have larger control volumes, causing faster heat spreading across the domain, therefore predict faster melting compared to fine meshes, which resolve the thermal gradient more accurately. So in this slide, I'm gonna give a summary to all my three slides above and then conclude it. So we realized that the mesh refinement improves accuracy. So for finer meshes at 2N and 4N, capture the melting and heating behavior more accurately with more time as opposed to the coarse mesh, which melted much faster. So for energies for residual graph, the energy conversion is smoother with finer meshes. So the residual oscillation reduced with finer meshes with more convergence happening, showing better numerical stability during the phase changes. And for final results consistent across all meshes. So for all cases, it achieved one. So the volume fraction achieved one at around 2 hours and stabilized at 310 Kelvin, which was what we said at 10,800 steps. Finer meshes reach slightly slower and more smooth and accurately as expected from the real life. And that's it from me. Thank you for listening.
Setting up the simulation, I've changed a few aspects. I turned on energy, I made the viscous laminar, I turned on solidification and melting, I added a material PCM, which I've stated its properties. I added a boundary condition, the heat flux input, which is where the heat is received. I also added a volume fraction plot so I can see when the PCM is fully melted. For my solution method, I used simple, least square cell-based, Presto, second order upwind, and first order implicit transient formulation. Changing the number of elements in a mesh results in varied stability, accuracy, and computational power. As my elements increased, my graphs stabilized to a lower value more quickly. Comparing the coarse graph to the very fine graph, the latter's data is more consistent throughout the entire measurement period. The fine graph can be seen to be in between the coarse and very fine graphs in terms of stability and accuracy. The volume fraction graph represents how much of an object is in a particular phase. In this case, how much of a PCM is liquid/melted. Once VF equals 1, the PCM is fully melted. My PCM begins to melt at 53 seconds and is fully melted at 446 seconds.
Here I have my simulation setup consisting of 3 different size meshes, which has been listed in the middle below. I also have my simulation thermal properties, which have also been listed right above it, with every detail for every mesh in these screenshots provided on this slide. Here I have my volume fraction and temperature graphs. For all 3 meshes, I ran for a total of at least 7,200 time steps, and we can see through these 3 graphs that all of those temperature graphs have a consistent time of about 5,000 flow time seconds before it reaches about 308 degrees Kelvin. And with the volume fractions, only the 2N mesh, I only had time to run that till above 1 volume fraction, but most of the simulations I ran beforehand with different sizes had similar results, with the flow time being around 5,000 till reaching the volume fraction as 1. Here I have my residual graphs. I did not take a copy of the 2N mesh for some reason, due to some file issues. However, my 4N and N mesh have both been copied with a residual graph. Both energy levels show consistency within its levels, and as mine is a 2D mesh, the velocities are going to be quite inaccurate, or rather redundant, because my energy levels should not be oscillating to any point, meaning that all of the energy should be converged. However, I shouldn't have any discrepancies within the data.
On the first slide, we can see the properties of the PCM and the different sizes of meshes that we used. All the properties on the left hand side, such as density, specific heat and thermal conductivity, all affected the final results of the simulation. When it comes to mesh sizing, each new mesh has double the number of elements as the previous mesh. This slide shows the simulation setup. When we look at the models, the main three changes that have occurred are: energy has been turned on, the viscous has been set to lamina, and solidification and melting has been turned on. We added a new fluid called PCM with all the properties shown on the previous slide. And the boundary conditions were set to all three walls of the PCM. For report definitions, we added two new definitions called temperature and volume fraction. These also can be seen in the residual and report files. These graphs help us determine the volume fraction and the temperature at which the PCM melts. After initializing the mesh, we set the calculations and the parameters. For the parameters, we have the number of time steps to be 7200 and the time step size to be 1 second. The maximum number of iterations used was 20. On the two slides above, we can see the residual, pressure fraction and temperature graphs for the three meshes that were used. And on this slide, we can see the main observances that were seen during these simulations. We can see that residuals for continuity, velocity components and energy converge steadily, with minor oscillations observed in the residuals later stages. And the stability has significantly improved from the initial transient fluctuations. In all three temperature graphs, the temperature increased smoothly and then plateaued at 310 Kelvin across the simulations, confirming successful phase change in the simulation. Also, the volume fraction of the liquid steadily rose to 1, which is the complete melting point in all cases, with a rate of increase depending on the flow rate. We were also able to observe smooth and faster convergence in finer meshes, consistent with better thermal transport.
For this study, I created 3 different mesh densities to observe their effects on the simulation. The coarse mesh had 510 nodes and 288 elements. The fine mesh had 10,050 nodes and 624 elements. And the very fine mesh had 2,108 nodes and 1,440 elements, providing the highest details. In this simulation, I modeled a phase change material using ANSYS Fluent. The PCM was defined as a fluid with a density of 815 kg per meter cube, a specific heat of 2000 joules per kilogram and Kelvin, and a thermal conductivity of 0.2 watt per meter Kelvin, I activated the solidification and melting model to simulate the phase change process, setting the solidus temperature at 302 Kelvin and liquidus at 308 Kelvin. The flow was set as laminar with no radiation or multi-phase interactions. Internal and a heat generation boundary was applied to drive a phase change. Residual temperature and volume fraction were monitored to assess convergence throughout the simulation. When looking at convergence, the coarse mesh initially looked stable but eventually diverged sharply, making the solution unreliable. The fine mesh actually showed worse behavior. The energy residue fluctuated heavily and never fully stabilized, making it quite unstable overall. However, the very fine mesh gave the best results with very low and flat residue throughout the simulation, showing excellent convergence. Overall, only the very fine mesh achieved a fully stable and accurate simulation. Even though the fine mesh has small elements, it was still not fine enough to properly capture the strong temperature gradients during phase change, which caused instability and fluctuation in the energy residual. This slide shows the volume fraction and temperature results for each mesh. In the coarse mesh, the graphs are smooth but have lower resolution. In the fine mesh, the curves are smoother and better resolved, especially for temperature. However, in the extra fine mesh, although the volume fraction is still smooth, the temperature graph becomes very noisy and unstable. This suggests that while finer meshes improve accuracy, if not handled carefully, they can also introduce numerical instability, especially in phase change simulation. Thank you. In conclusion, as the mesh was refined from coarse to very fine, the overall accuracy and convergence of the simulation improved significantly. The coarse mesh failed to maintain stability, while the fine mesh showed instability due to insufficient resolution for capturing phase change effects. Only the very fine mesh achieved reliable convergence, though it introduced some temperature instability due to numerical sensitivity. The volume fraction result consistently improved with finer meshes, but temperature prediction become more sensitive and very fine scales. Overall, this study highlights that careful balance between mesh density and solver setting is critical to achieving a accurate and stable phase change simulation. Thank you.